The force of electromagnetism is governed by four fundamental equations. These equations are collectively known as Maxwell's equations. Maxwell's equations successfully explain all electromagnetic phenomena and all applications of the force of electromagnetism. Throughout the remainder of this course prior to the AP exam, you are introduced to these four equations. The first of these four equations is what is called Gauss's law. As you'll see, Coulomb's law is actually a specific application of a more fundamental expression, that is, Gauss's law. In order to explain Gauss's law to you, however, we have to define a new quantity, what is called flux. I'm going to define flux for us, not in terms of electric fields just yet, but instead in terms of water. So let me go ahead and describe what is meant by a water flux. Okay, let's say that I have water flowing downstream. I'm going to represent that as a series of field lines, as a series of vectors, like so. So let's say that water is flowing downstream like this. Okay, now there are two properties associated with this water. First of all is its density. Because it is a three-dimensional object, we'll go ahead and write the density here with the Greek letter rho. And then we have these vectors themselves, which we'll picture as velocity vectors. So then therefore we have the velocity vector v here associated with the water as it flows downstream. Okay, now what I'm going to draw here perpendicular to these field lines is an area. So for example, imagine this rectangle, and then I look at this rectangle like so, face on like so, in the direction that the water is flowing. So let me go ahead and draw that area. We'll just simply refer to it as A, like so, and it's perpendicular to my field lines. Okay, now the water flux by definition is the following expression. First of all, flux is always denoted with the capital letter phi, and because we're talking about water, let me go ahead and write that word. Okay, by definition, the water flux that is passing through this area A is as follows. Rho v A, like so. Now to get a handle on exactly what this expression is saying, it's useful for us to check the units. So let's go ahead and do so. Okay, first of all, we have density. Density, of course, is mass over volume. So then therefore, we'll write that as kilograms per meter cubed. And then we'll multiply that by velocity v. That's in terms of meters per second. Okay, and then we'll multiply it by the area. Once again, that's the area of this rectangle, for example. That would be in terms of meters squared, like so. Okay, notice very simply that all the meters cancel out here, like so, and then what we're left with is kilograms per second. So the easiest way to picture this is it's as if you're standing on the side, for example, of a stream, and you're just watching the water go by, and it's the number of kilograms per second that passes through an area right at your location. That's the easiest way to picture this. Okay, now, it's useful for you at home to do the following. Take a rectangular sheet of paper, for example, such as my cardboard here, and then hold it such that you look at it face on as I've drawn here on this diagram. And then the flux that you see through this area A is described by this expression. But now what I'm going to do is I'm going to take the rectangle and I'm going to tilt it on an angle like this, such that the bottom is tilted away from me, like so. And then take a look at the area that you see with your eyes. Once again, it's insightful for you to do this at home. Take a piece of paper, hold it out like so, hold it perpendicular to yourself first, and then secondly, tilt it on an angle like so. Is the flux through the area that you see the same as this quantity here? No, it's a smaller number. The easiest way to picture this is to once again take the piece of paper, tilt it on an angle, and then in between your index finger and your thumb, kind of pinch the top portion of the cardboard and the bottom portion of the cardboard like so. And then right here is the area that I see like so, that for example, the water is passing through. It's an area that is smaller than the area A on this diagram. The easiest way to visualize this in terms of a diagram is to now draw the following. Okay, I'm going to draw the exact same field lines as I did on the top board. Same number and same spacing between them, like so. Okay, but now I'm going to take my green area A that I have on the top board and tilt it on an angle, like so. It's the same area A as before, but notice that there are less field lines that are passing through it as opposed to what we had on the top board when the area A was perpendicular to the field lines. What is then therefore the area, if you will, that the field lines are passing through? Well, it's this area right here on the diagram, like so. I'm going to go ahead and construct the right triangle here, and then let's go ahead and define an angle here as theta. This right here was the area that I was pinching in between my fingers. Once again, it's insightful for you to do this at home. Take a piece of paper or the cardboard, tilt it like so, and then pinch the top and bottom like this between your fingers as I'm doing here. Right here in the space between my fingers is this distance, if you will, on my diagram. Notice that this right here is a cosine theta. So then therefore the water flux in this case is not rho VA, instead it's rho V A cosine theta. And notice that this quantity here is a lesser value than it is on the top board. Here's immediately a real-world application for you of flux, not in terms of water, but instead in terms of light. So for example, why is it cold in the wintertime as opposed to being, say, warm in the summertime? Well, in the summer, the sun is higher in the sky. So then therefore, when the sun is higher in the sky, the flux is greater over a square area. However, in the wintertime, if the sun is low in the sky, then it's as if I'm the sun and I'm looking at the piece of paper like so on an angle. This right here is the area that I see. Therefore, what this then means is that the energy per second is spread out over a wider area when the sun is low in the sky. So if I'm the sun and I'm high in the sky, I see the area is A. If I'm low in the sky, I see the area is A cosine theta, and therefore the flux is less. So that's the reason why it's cold in the winter, is because when the sun is low in the sky, you receive less energy per second per square inch of surface area on the surface of the earth, okay? All right, at any rate, however, getting back to our calculation here, once again, the flux that is passing through this quantity now of A cosine theta is described by this expression here. Now, mathematically, I'm describing a specific type of multiplication here. Take a look at this quantity carefully. What type of multiplication is being described there? It's a dot product. It's specifically, however, the dot product between the following two vectors. The velocity vector V, and now an area vector A. What is the area vector A? Well, let's go back to this diagram here. Okay, on this diagram, right here is the area, and then drawn perpendicular to that, like so, is another vector. This right here, by definition, is the area vector A. In which direction the area vector A points, that is like so or like so, well, I'll get to that in a little bit more detail a little bit later on, but suffice to say it ultimately obeys right-hand rule. We'll get to that later. Once again, the area vector A is perpendicular to the area itself. The area itself is right here originally in green. Okay, now here's my angle theta from a few minutes ago. If you futz around with the geometry, and then this black dotted line here is parallel to the blue velocity vectors, you can easily show that this angle here is actually the same thing as this green angle. This right here is the angle theta. So then therefore the water flux that's passing through this A cosine theta is ultimately described by this dot product. Now I'm describing water flux to you thus far by drawing the area A as a straight line, for example, on these diagrams. But it doesn't necessarily have to be a straight line. The area, for example, can be any shape that I want. So then therefore, for example, let me draw this. Okay, once again, let me draw the same three field lines that represent the water. Like so, density rho, velocity vector v. But now let's say that, for example, I do something like this. That right there is ultimately my area A. How would I then go about performing a flux calculation through this area where it's not being described as a perfectly flat plane, for example, like I was drawing earlier? Well, what I can do is the following. For example, right here at this location, perpendicular to the area, is a little infinitesimally small area vector dA. And then what I can do is calculate the infinitesimal amount of flux that is passing through that infinitesimally small vector dA in the following way. Like so. And then of course to get the entire flux through this green area that I've drawn here, then ultimately we would have to integrate all of these infinitesimally small area vectors dA. So then therefore ultimately the water flux would be described by the following integral. Let me write this out correctly. There we go, like so. This is an area integral. It's a double integral because we're integrating over an area as described by the infinitesimally small area vector dA. This is an example of a double integral. It's sometimes referred to as a surface integral. Okay, now, the area that I've been describing thus far, up to this point with these diagrams and so on and so forth, is a specific type of area. It's referred to as an open area. Okay, geometrically speaking, an open area has an edge to it. So, for example, we have here this rectangle. Imagine starting somewhere on this rectangle. Let's say you're standing here and you start walking. You eventually come to an edge. What that means is that the area is open. The area has an edge. Okay, now let me describe to you what is meant by a closed area. Okay, a closed area is an area that has no edge. So, for example, imagine being on the surface of a sphere. After all, you're right now on the surface of a sphere. And then you start walking. Are you ever going to come to the edge of the earth? No. And the reason for that is because the three-dimensional sphere has an area, a surface area associated with it that is closed. It never has an edge. So if you walk on the surface of the earth, you're never going to come to an edge. The area has no edge. So now let me calculate the flux of water through a closed area. Thus far, what I've been describing is through an open area. Let's see what happens through a closed area. Okay, now I'm going to do the following. Let me do some erasing here. Okay, and then I'm going to once again draw my field lines like so. Rho V. And now let's say that I draw an area that is somehow shaped like this. So you have to think of it in terms of a three-dimensional object, like a sphere or something like that. So there's a portion of the surface here, there's a portion of the surface here. And then what we want to do is we want to calculate the total flux through this closed surface. Okay, first of all, mathematically, here's how we write this. The flux of water through this closed surface is equal to the following integral. Notice this little symbol that I added here to the integral sign. This indicates that the surface area, the area itself, is closed. So this little circle that I drew here means that we're specifically talking about a closed area. So if you want something that's easy to visualize here, just picture it, for example, as a sphere. And then we're going to calculate the total flux of water through that sphere. Before I write down the answer and tell you why it is, what is the answer? It's obviously 0. It's 0 for the following reason. Think of it mathematically, first of all, in the following way. Let's say over here on this side of the diagram, perpendicular, like so, we have the individual area vectors dA, like so. And then therefore, if we were going to calculate the water flux on this side of the diagram, we would end up with a positive number. By the way, at this point, I can now very carefully define the direction of the area vector dA for a closed surface. For a closed surface, the area vector dA, by definition, goes from the inside out. So then therefore, that's what I've drawn here in black. These perpendicular dA vectors, they're going from the inside out of the surface itself. So suffice it to say, on this side of the diagram, we would calculate a positive flux when doing this dot product. However, take a look at the other side of the diagram. So here's a little dA like so. Here's a little dA like so, and so on. And keep in mind that the blue velocity vectors v are pointing in this direction, like so. So then therefore, what type of number would you calculate then when calculating the dot product, for example, between these two vectors? It would be a negative number. So ultimately, you would have a negative flux going in, and it would be exactly canceled out by a positive flux coming out. Therefore, as long as there is no source or sink of water within the closed area, the flux going in is the same as the flux going out. The number of blue lines going in is the same as the number of blue lines going out. Therefore, the total flux through the closed area is equal to 0. Okay, now I kind of gave away the answer a few moments ago. What would be necessary within the area for the total flux to be a positive number or instead a negative number? What is referred to as a source and a sink. For example, let's say that I draw this. Okay, once again, I'll start with just these three field lines, like so. Okay, here's my closed area, like so. But now let's say that I have more lines coming out of that area than going in. Like so. So then therefore, what type of flux, positive, negative, or 0, would I calculate in this case? Once again, the flux passing through the closed area. In this case, very obviously, it would be a positive number. What is necessary for this to happen? How could you have, in other words, more water coming out of the surface than going in? Well, you would have to have a source of water within the surface. This is what is just generically referred to as a source. If you want to think of it in the context of water, it's like there's a faucet or something like that somewhere contained within this area, such that more water is flowing out of it than is flowing in. So then therefore a source is necessary for the flux to be a positive number. So a source of water within the closed area is necessary for the flux to be a positive number. An example would be a faucet if we're thinking about it in terms of water. Faucet, if I can spell the word. There we go. Okay, now, what is the condition necessary for the flux to be instead now a negative number? Think of it like this. Okay, once again, initially here, I'll just draw three lines. Like so. Okay, here's my area, like so. But now let's say that I have, let me put the additional arrows associated with these vectors over here so we can picture this a little bit more easily. Let's say that I have additional lines going in, like so. So I have more lines going into the area than coming out. So then therefore, some of the water is disappearing, if you will, from somewhere within this area. This is just generically referred to as a sink. like a drain, for example, or something like that in the context of water. So in this case, the water flux would be a negative number, and then a sink, as it's called, of water within the closed area is necessary. Once again, in the context of water, a nice example of this would be a drain. Okay, now in the next lecture, we'll essentially take the ideas that have been described here and apply it not to a flux of water, but instead to an electric flux. That is, in terms of electric field lines, as opposed to lines representing water flowing downstream.